I still write a compiler for a small imperative Oberon-style programming language called Elna, and I slowly move into the direction where we implement parsing complex types to procedures. So current procedures can accept only arguments that feed into the registers, but not aggregates like static arrays or records. And they cannot also return such arguments like aggregates. I have already done the first thing needed, so I allowed aggregates to be allocated on the stack so that we can define local variables of type like static array or record. And now we need to allow these types also as return types and as arguments. And the first thing that we will need for that is the return type for the procedures. So current procedures implementation, they are only procs keyword, procedure name, and the list of parameters, and that's it. After that, we should parse the return type because we will need it to construct the return value properly. So we should be able to parse the return type. The return type will be separated from the argument list by an arrow. This is different than languages like Pascal or Oberon that use semicolon. Semicolon is a bit difficult to read if we have functions as arguments. So I later want to support functions as arguments. So that would mean that, for example, a function that gets an x has a signature like this and returns an int, for example. The signature with a semicolon as separator would look like this, where we have one semicolon here for the argument name and here for the return type, and it is a bit difficult to read. I think that much easier to read in these cases is an arrow, and therefore I'm going to use arrow as well for normal procedure declarations, or these procedure headings basically. I have a token for an arrow, but that is actually so we need to extend the tokenizer so that the tokenizer can read this token, this arrow, from the input stream, and after that we can parse this thing. Execute the action next transition. So an arrow is a minus followed by the greater than sign, and I think that I can already, so here read the minus. But this is actually a different thing. This classifies a single sign token, a single character token. This so what is the difference here? This token, this classifies single functions that are tokens that are always one character, and these tokens can have more characters. For example, greater than, greater can have an equal sign after that, and minus can have a greater than sign after it. Let us see where it is called. Action to perform, if it is thinalize. Composite. Exactly, here we check whether first character is colon. Then this is an assignment. If it is greater, I do not check for the assignment. Actually, I should check here whether the current character is also assignment, the last character, but I suppose assignment is the only composite character. And actually we can check here whether the first character is a minus. Then I actually think that we have only one composite that starts with the minus sign, and that would be actually this Elna Lexa kind arrow. Unary expression. I want to find the code there, the classification table. So this is the parser, the tokenizer for the keywords. Number sign state. These are different states of the tokenizer. And for the minus, we will probably have its own class. And it sets the lex in the minus state. Yeah, I think this is already implemented. So here we are in the minus state, and if we see minus, we call the finalize action and go into the finish state. I'm not sure this is actually what is with great. With great we do the same. Yes, it should work. So my tokenizer is implemented as a state machine where I describe each state, for example, and each token starts a state machine, and it goes from the start state into the minus state, and into the minus state. When we see minus, it can be only this minus, or it can be a minus greater than. In which case set transition, exactly. So default transition, if we see something, then it is just minus, and we do the finalize action so that we save this minus as token. And if after this minus we see a greater sign, then this is then we call the composite action, and it creates a token arrow. So this should actually already work. I don't think I do anything else, so we can test it. For the test, I cannot test it in this stage because the previous version of the compiler cannot compile it. I do not know if I already created a new stage. No, I haven't. So let us create the stage 20 just for testing. For that, we just copy the current boot stage 19 into boot stage 20. I think that I shouldn't need anything else. I only want to also edit my rake file so that I can... Oh, this is already done. So I had already the 20th stage before for testing. I have a rake file that copies stage 19 into stage 20, so I can update it a bit more easier. This line is actually not needed, but I think it won't break anything. So now we can go into the stage 20, and we can, for example, create procedure F that returns a word. No, it cannot be parsed. We should extend the parse. Of course, I only implemented it in the tokenizer. So we go to the stage 19 and go to the parser. So here we have the procedure declaration. Procedure name, open paren, close paren, skip, and here we will see a semicolon or an arrow with a return type. So after we read this token, we do not just skip it, but we check what is this token. If token kind is an Alexa kind, I think is the proper enumeration type. Alexa kind arrow. Then and else we just keep the actually we can skip this token anyways, it doesn't matter because we cannot do with the with the arrow anything. We just have to pass the thing after that. That means that if it is a semicolon, then it is already handled, and if it is an arrow, then we have to parse a type expression. I should have type expression somewhere here, but I call this variable declaration function. Let us look into this function since it will contain the name or the type expression parser variable declaration, and it reads the name. Elena parts the type expression. So otherwise we can call this Elena parser type expression. This already should be enough to do the parsing itself. We will test it first, and then so we can copy the current stage into the 20th stage. Then we go into the stage 20 source code, and we define this function procedure f with the return type word and an empty body. We are just interested to see whether we can compile it or not. And I have to recreate the Ninja file. So let us remove it. This is build Ninja, and after that we can regenerate the Ninja file. And now I can rebuild the two last stages. Okay. That looks actually fine, I think. Yep. So now we can parse. Return type. And another thing that we need, so we want to save the return type, of course, somewhere. For that we find the procedure declaration. It has tree kind, the next element, the next procedure, because procedures are a list. It has name and name length. It has body, probably a list of statements. It has local variables, and it has parameters. And I think that we can just add another member to the record, and probably just call it return type. I wonder what is parameters. This should be pairs. So the parameter name and parameter type. This should be actually somewhere here. So here we assign the temporaries, and parameters should be somewhere before variable declaration. If parameter head, result parameters is parameter head. This parameter head is L03 declaration. Okay. So here we have type declaration. I wonder, declaration has kind, next, name and length. The most generic type is actually this L03 type, and for now we can just put it in here. So a pointer to the L03 node type. This will be, because somehow I think that I do not have a type for the type expressions for whatever reason. How do I actually parse this type expression? The function will probably create the type expression. So if I go to this procedure, it is here, and it parses one of the types and just returns it. Well, so let us go to this Parsing named type expression, and it allocates this L03 named type. So actually it should be called L03 type expression, but we do not have it. We have a special type expression like named and record type expressions and pointer type expression, but not a generic type expression yet, and we do not need it just now, so we will leave it as is for now. So the return type will be just ignite node. And now we want to go to this procedure again that did the parsing. It was procedure declaration parser. And here we need to assign it to the result. Return type. And we assign the parse expression to it, and actually we do need an else statement, and in else we will assign a nil to it. That should be it.